Good afternoon, and welcome to the 6th Boston University Dialogues in Biological Anthropology. Everybody who has ever given serious thought to the facts about the world of organic nature, from Aristotle on down to the present, has always been struck by the fact that animals and plants are minutely suited to survive and live and prosper in their environments and in the ways of life that they follow in those environments. In other words, that life is adapted to its circumstances. One of the great strengths of Darwin's theory was that he provided not only an explanation of how those adaptations could have originated, but also of the otherwise perplexing and annoying fact that those adaptations are very frequently quite imperfect, and that to many of us, it seems in many cases, we could have thought of a better idea ourselves. Human beings share a lot of key adaptations that have contributed to and help explain our tremendous success and our biological uniqueness among all the animals of the world. These include things like our bipedality, our large complex brains, our long lifespans, our slow life histories, and so on. But this legacy of very successful adaptation comes with costs. Many of these adaptations have undesirable side effects that we still suffer from today in our present biological circumstances in the 21st century. In 1951, the biological anthropologist Wilton Krogman published an article in Scientific American that detailed some of these drawbacks of the kinds of unique adaptations that human beings have. And he entitled this article, "The Scars of Human Evolution." We're privileged to have with us today, in a departure from our usual format in these dialogues, a preview of an upcoming symposium at this weekend's Boston meetings of the American Association for the Advancement of Science, a symposium that updates and commemorates Krogman's article. We've brought them here today to share with us some of the things that they have to say about the drawbacks and the design failures of human uniqueness and human biology. So today's dialogue in biological anthropology is entitled Unintelligent Design, The Scars of Human Evolution. Our first speaker in this symposium preview is one of its organizers, Professor Rachel Caspari from Central Michigan University, who's going to talk to us about the scars of human evolution, recent longevity, and its consequences.
Well, thank you very much, Dr. Cartmill and Kay Brown, for inviting us here. It's wonderful to have this opportunity to preview our symposium that we will be presenting tomorrow. All you need to do to be convinced of the veracity of unintelligent design is to be lucky enough to live a long time, because basically any of the scars of human evolution that Wilton Krogman discussed in his 1951 article will become extremely apparent if you survive to be an older adult. Today, what I'd like to start the symposium off with is a discussion of longevity, in a sense, and its relationship to these scars of human evolution, and to address a couple of questions that will probably come to people's minds as they listen to the rest of the speakers in the symposium. One question is, to what extent did these scars of human evolution affect ancestral populations? And a second is, why haven't they been eliminated by natural selection? There is clearly a relationship between these scars and human longevity. You can see this in the orthopedic problems and other correlates of bipedalism, which will be talked about later on by Bruce Latimer and Jerry DeSilva, correlates of the obstetric dilemma that will be discussed by Karen Rosenberg, and I will talk a little bit more about some of the problems with pelvic organ prolapse that is both a consequence of living longer and a consequence of giving birth to large brain babies. And we can talk a little bit about the scars that are associated with longevity itself. And to start, we can ask, to what extent were these present in ancestral human populations? One of the sites that I've worked on is a site in Croatia called Krapina. This is a Neanderthal site that dates to about 130,000 years ago. It was excavated at the turn of the last century by a great paleontologist called Gorjanovich Kramberger. And in this slide, you can see the stratigraphy of this site. What's cool about this site is that there are the remains of, it yielded the remains of a large number of individuals, perhaps as many as 70 to 80 individuals. And the site was deposited very rapidly. So although you see this very long sequence here, the hominids, the Neanderthals, actually come from a very limited zone on this site. So for paleontological samples, this is the closest you can kind of get to a real sort of population. It's the sort of thing that you could possibly do demography on. It yielded the remains of about 200 isolated teeth among many, many other fragments. Many are associated as, quote, dental individuals. These are teeth that belong together because they belong to a single individual. Some are housed in mandibles and maxillae, and there have been between 75 and 83 individuals recognized from this. And this is a very large population for fossils. The age of death has been estimated by colleagues of mine and myself using the Miles method ages, which is based on attrition, basically wear stages, based on an assumption about dental eruption patterns. And I'm just showing you some of the ways that this has been used. And also using micro-CT scans, basically high-resolution micro-CT images of the internal structure of teeth, which has been used to corroborate some of the ages that are based on attrition. These are independent ways of assessing age at death. And in both cases, we have a very good concordance of dates, of ages of these fossils based on these two very different kinds of aging techniques on teeth. One is secondary dentin, which is basically the secretion of the development of secondary dentin in the pulp chamber of teeth, and sclerotic dentin as well we've been looking at. And you can see this in the image. In the image to the left, you can see how there's been secondary dentin built up in the pulp chamber. This can be resolved by looking at relative pulp volumes, as you can see in this tooth on the left. And this slide here shows the concordance between the Miles method ages based on attrition and relative pulp volume. Using these data, we've been able to develop a Crapina age distribution for the Neanderthal fossils that are found there. And what you see are the numbers of individuals that survived into the different age categories that are labeled on the x-axis. This was transformed into a survivorship curve. We estimated the number of missing infants, because infants do not fossilize well, estimating the number of missing infants based on some modern archaic sites. And what you can see here is a survivorship curve for Crapina, and you can see that it is very steep. These are the numbers of individuals that would be surviving to these particular ages. Okay. Compared to even a modern archaeological population living to about 1,000 years ago. This one is from a site called Libin. If you look at the demography of that site, even that, which is a site which had very, very high mortality for modern humans, you can see that the Crapina survivorship, the Crapina survivorship curve is far, far steeper. It had much, much higher mortality than you would expect to see in any kind of living population. So you could say, well, that's one fossil site. That's pretty awful. But how characteristic is that of other fossil sites? And there are, of course, very few fossil sites that can give you that kind of demographic information. But of those that exist, they all sort of give you the same kind of data. This is a comparison of the Crapina curve with one from Cima de los Huesos in Atapuerca, Spain, and it's a very, very similar sort of survivorship curve. They basically also have very, very high mortality. And so this doesn't seem like it's necessarily such an ancient thing. Also, the very oldest of the Neanderthals at Crapina, the very, very oldest, are very similar in terms of their wear pattern to the very oldest Neanderthals that we think about generally. This is the Crapina O tooth, which is one of the oldest of Crapina based on dental wear, and it's very similar in terms of attrition to La Chapelle, the old man of La Chapelle, one of the older Neanderthals known in the entire record. So it seems like what we might be looking at here is an archaic life history pattern, basically, where you have a very, very high level of young adult mortality. Okay. We've also addressed the broader context of this, which can be quite difficult to do when looking at a very, very large sample within the fossil record. The problem, of course, with this is that traditional aging methods lose accuracy with older individuals, and you can have potentially different maturation rates for different fossil samples. So working with a good colleague of mine from the University of California at Riverside, Sang-Hee Lee, we developed a method a few years ago that circumvented some of these problems. And we called this the OI ratio, the ratio of older to younger adults in the distribution, where we basically lump a lot of fossils in together so that we look at, instead of looking at the exact ages that people live to be, we essentially are asking the question, how many people live to be old? So we just looked at the numbers of young adults, people that we aged to between 15 and 30, and those that were over 30. And we looked at a ratio of older to younger adults. This circumvented many of our problems. First of all, low resolution was actually okay. The broad categories gave us large samples, and we were able to accommodate these different maturation rates. So basically, we assessed adulthood as the age of third molar eruption, and older adulthood as double that age. This is a friend. Basically, it's the age that one could potentially become a grandparent. Okay. Oops. Okay. So what we found was that OI ratios basically increased dramatically in the last 30,000 years. The Neanderthals, and other archaic humans, have very low OI ratios. Neanderthals at about 0.4, which means that for every 10 young adult Neanderthals in the death distribution, there are 4 older adults. In comparison, for Upper Paleolithic folks who were living at about 30,000 years ago, the people that were following Neanderthals, you've got OI ratios of 2. And that means that for every 10 young adults in the death distribution, you have 20 older adults. And this is something that you see in modern populations like Libyan. For instance, Libyan's OI ratio is 1.9. This is something that is really quite important. So you see the significant increase in the proportion of surviving old adults in the death distribution, but you only see it very, very recently. Prior to that, very few people lived beyond what we think of as age 30. So this is really quite a big change. This happened in the Upper Paleolithic, a time that's associated with all sorts of other kinds of archaeological changes. And one question is are we actually looking at the difference between two different species, Neanderthals and modern humans, or are we looking at the difference between two different cultures, Middle and Upper Paleolithic? And we resolved that by looking at the West Asian Middle Paleolithic. So these are people that were not making these fancy tools associated with the Upper Paleolithic, but you have both Neanderthals and modern humans that were basically existing at the same time. They have the same OI ratios, well below the OI ratio of 2. So there are selective advantages of longevity. We decided that basically there were a lot of reasons why, even at the glacial maximum, at a time when it was very, very hard to stay alive, you had people surviving to older age. And the idea is that older people were valued. There was some kind of selective advantage to being old. But of course, longevity has its scars. And the rest of my time today, I'd like to discuss what some of these scars were. But they were scars that were not probably affecting people prior to about 30,000 years ago, at least not people in large number. One is somewhat, of course, you'll be hearing about today. You'll be hearing a lot about orthopedic problems that certainly affect younger individuals, but they affect people who are older far more frequently. Another thing that is associated with bipedalism is pelvic organ prolapse, which is associated with bipedalism. It's also associated with childbirth, and it's associated with age. And risk doubles with each decade of life. Over 50% of women over the age of 45 are affected by pelvic organ prolapse. This can be procedentia, which is when the uterus falls into the vagina, basically, and it can cause severe problems. But there can also be intrusions of the bladder, the small bowel, the rectum, all of these things into the vagina, and these can be very, very miserable conditions. Associated with this is also urinary incontinence. It's caused also by the weakening of the pelvic floor muscles, but it's also caused by an age-related decrease in the striated muscle fibers in the urethra walls. And if you live long enough, basically, you can lose even up to 65% of those fibers. And so if you live long enough, you will suffer from urinary incontinence. There's no question about it. Another issue is osteoporosis that I suspect others will be talking about today, but this is clearly associated with age. It's associated with just the plain bone loss associated with age, and it's of course much more prevalent in women because there's a huge menopausal decline in your bone density. Osteoporosis is defined by having bone density 2.5 standard deviations below the adult peak mean, I guess. But so you have the bone loss that's associated with age, you have bone loss that's associated with menopause, and but it's also associated with the amount of your bone mineral density in young adulthood. So if archaic populations had more dense bone, they would be more unlikely also to suffer from osteoporosis. There are clearly scars that are associated with living longer that are just a part of the epidemiological transition, basically the chronic degenerative diseases that are associated with that. But there's also scars that are associated with the demographic consequences of the initial increase in longevity. Adam Van Arsdale of Wellesley College has done some modeling of looking at the demographic parameters associated with OI ratios, and I won't go into all of the things that he did in terms of developing the mortality statistics, etc. But what he noticed was that in order to sustain the birth rate that would be necessary to sustain archaic populations with OI ratios of 0.4, you would need to have a total fertility rate that was 20% higher in earlier populations. If you maintained that fertility rate when the mortality rate decreased, right, you would obviously have population growth. Population growth would be inevitable. So this increase in adult survivorship has huge demographic implications. It contributes to population stability, but more importantly for this discussion, it contributes to population growth and expansion. For two reasons, both the increased fertility, because people are living longer, and also because of what people have called the grandmother effect, basically, older people taking care of their offspring. The effects of population growth could give rise to infectious disease, as we know, that became even more prevalent in the Neolithic as populations grew further, and of course increased population density and expansion. And of course it also increased our rates of evolution, which is the topic of another discussion. So with mortality decrease, populations expand. OI ratios in developed countries now are extremely high, over 100. In some places. Think of a cemetery. You aren't going to find very many people between the ages of 15 and 30 in those cemeteries. So you're going to have very, very high OI ratios now into the hundreds. So what that means is that the scars of human evolution are now affecting more people than ever before. And I will leave it right there. Thank you very much.
Thanks very much, Rachel. We're going in the succeeding 4 talks in today's symposium preview to follow a rising trajectory. We're going to begin with the feet, work our way up through the pelvis, into the vertebral column, and finish with the teeth. And so, therefore, our next speaker is one of my colleagues here at Boston University, one of the stars of our biological anthropology program, Jeremy DeSilva, who is going to talk to us about the feet and the evolution of the human foot under the title of Starting Out on the Wrong Foot.
Thank you very much, everyone. First, happy Valentine's Day. And slides? There we are. Sorry about that. Happy Valentine's Day, especially to Erin. Thank you very much, Matt and Kay Brown, for organizing what promises to be another very successful dialogues in biological anthropology. Hopefully, we'll see some of you that are tuning into the webcast here at 5:30 for the panel discussion, which I can promise you will be quite illuminating and entertaining. I want to take things south, as Matt mentioned, and talk about the foot, and talk about some of the problems that we have, in part because we walk on modified ape feet. Evolution only works with the material that it has, and we are apes. We have evolved from ape-like ancestors, and therefore the starting point that we have to discuss is this ape-like foot. And it has its consequences. It has consequences that has led podiatry to be $1 billion industry. And so in order to talk about the evolution of the foot, we're going to go back millions of years, of course. But before we do that, I just want to take us back into the immediate future and discuss last year's Olympic Games. Most of you tuned into the Olympic Games. Close to 1 billion people watched the Olympics last year in London. I certainly watched them. And they were wonderful performances that we saw of humans doing things that seemed to be beyond the range of possibility for humans. They were feats of strength and speed and endurance that were just remarkable in the pool and on the track and in gymnastics arenas. But there was one performance that I think stood out amongst the others in the sense that it was a performance of a sprinter, a South African sprinter by the name of Oscar Pistorius, who didn't have feet. Now, those of you who tuned into the news this morning know that Oscar Pistorius should not be discussed in terms of his character, perhaps, so we're going to stick to just his feet and the prosthetic limbs that he was using when he raced around this track as fast as just about any human being on the planet. And one of the things that I thought was quite remarkable about these prosthetic limbs, and maybe you spotted this as well, is that they don't look much like human feet. And so the question that many people asked is, why not? Why don't these things look more like human feet? If we look closely at the prosthetic here, it's made of a single structure, and it is rigid enough to push off the ground and propel the runner into his next step. But it also has elastic properties that store energy and recoil and allow him to put a bit of a kick in his step. And many of these properties exist in the human foot as well, although the human foot, in stark contrast to this prosthetic limb, is made of 26 individual little parts, 52 in total if you count both feet, meaning that a quarter of our skeleton is made of foot bones. And this doesn't seem like a particularly good idea if you want to have a stiff, rigid structure to push off the ground with. So natural selection has modified this structure by thickening ligaments and changing roots of a few muscles through the foot and changing a few subtle anatomies of the foot bones themselves, what I would consider to be the biological equivalent of duct tape and paper clips. So we can ask ourselves, why? Why don't we, or why haven't we, given the power of natural selection, evolved a foot that's more like the Pistorius prosthetic limb? Because if we look in the natural world, we actually do see examples of a limb that's more like the prosthetic blade that was used by these athletes. Birds, for instance, terrestrial birds like ostriches, have fused together the bones of their ankle and the bones of their metatarsals together into a single bone known as the tarsometatarsus. They've reduced their pedal digits down to a single digit in some cases, or 2 or 3. And there are long tendons that course through the leg, which provide that elastic spring in their step. Most of the muscles of the bird are up in the body, which is going to increase stride frequency and therefore speed. Humans, in contrast, have a very different sort of design to their foot. And why is this the case? Well, I contend it's because birds have had a 230 million year head start on us. Birds have been bipedal for a long time. We can trace through the fossil record ancestors of birds that were bipedal, right through dinosaurs that were bipedal, right back to the ancestors of the dinosaurs, early archosaurs that were also bipedal. So natural selection has been refining and tuning the skeleton of these animals for bipedal locomotion for a long, long time. Humans, in contrast, we know from the fossil record, have only been bipedal for about 4 to 5 million years, so a shorter amount of time. But I don't think it's just about time. It also has to do with starting points and the anatomy from which natural selection can operate. So if we go back into the Mesozoic, if we go back into the time period where birds had their ancestors and mammals have theirs, what we find are these little mammalian ancestors, like this beautiful one here known as Eomaya, that was found in 125 million year old deposits in China. And researchers have studied the feet of these animals, and what they've noticed is that in most tetrapods, the talus and the calcaneus are right next to each other, which is going to promote motion in the sagittal plane, flexion and extension. But in these early mammals, what ends up happening is that the talus shifts to a position on top of the calcaneus. And I have my handy-dandy foot here. So what happens, and this is a human foot, what happens when the talus is on top of the calcaneus is you now have a different plane, the coronal plane, and you now have a possibility of motion in that plane because of this new joint, the subtalar joint. And it allows the foot to twist inwards and to twist outwards. And so this inversion and eversion of the foot introduces a new range of motion, more mobility, and more grasping potential for these little mammals that were probably scurrying around up in trees or down into little holes. So that's the foot from which early mammals evolved, but it is not a point of no return, because we do have examples of mammals that have convergently evolved the Pistorius blade-like structure. Cursorial mammals like artiodactyls or perissodactyls like horses, this horse here, for instance. Many of the bones of the ankle have shrunk down considerably. The bones of the metatarsals have fused together into a single rigid structure. They've reduced their pedal digits down to 1 in this case, and sometimes 2 in the case of artiodactyls. Long tendons course through these legs, and most of the muscles are up in the body of the animal. This should sound consistent or sound familiar, because we saw the same thing in birds. Now, these are not bipedal animals, but this one is. So it begs the question, why don't we see similar anatomies in the bones of the human? And it's, of course, because humans are primates. And over the course of mammalian evolution, in the beginnings of the primates, this already somewhat mobile foot became even more and more and more mobile and adapted for grasping up in the trees. As apes evolved in the Oligocene and into the Miocene, we now have these big animals that are climbing a considerable amount, evolving adaptations for mobility and grasping abilities of the foot. Now, we know from the fossil record, or at least we suspect, that the apes today, chimpanzees, orangutans, have evolved an even more mobile grasping foot from the common ancestor that we share with them. But even this common ancestor, something like a proconsul, for instance, had a highly mobile grasping foot. And that's our starting point. So what has natural selection done? Well, it's done a pretty decent job, I think, of stiffening up this foot and allowing it to remain rigid as it pushes off the ground and to have some elastic spring to it as well. But as I mentioned earlier, what we're looking at are paper clips and duct tape. We've got ligaments holding these bones together and no evidence of these bones fusing together in a way that you see in, say, an ostrich or in a horse or in a deer. There are consequences for this. For jerry-rigging this system the way natural selection does, sorry, I jumped ahead, there are consequences. And many of these consequences are things that we see in podiatry offices today. Sprained ankles, plantar fasciitis, heel spurs, shin splints, all sorts of problems. And if you haven't experienced them yet, you will. It's almost guaranteed that somebody at some point is going to have quite a bit of problems with their feet. Now, it is reasonable to hypothesize that one of the reasons that we have so many foot problems is because we wear shoes, we walk on sidewalks, and we're a bunch of couch potatoes. And if only we walked around with bare feet and ran through the rolling hills that maybe our ancestors were moving through, we would develop stiffer, tougher feet, and we wouldn't have as many foot problems. Now, one of the ways to test this is a reasonable idea. One of the ways to test it is to go back into the fossil record and to see whether we see the same kinds of foot pathologies back in the past as we do today. Now, there's no question that our modern lifestyle has probably increased the likelihood of injury, but we still do see problems in our ancestors in the past. For instance, the very famous Lucy skeleton, she preserves a nice ankle, and that ankle has a peculiar angle to it. And this is something that's been recognized for a considerable amount of time. But the explanation for it, I think, has been eluding us. So a colleague of mine and I looked at old podiatry films, and what we noticed was that humans today can have this same kind of angulation. About 5% of humans today have this same kind of angulation. And it's the humans today that have flat feet. So just as in humans today, you have individuals with very high arches and individuals with flat feet, as we go back to 3 million years ago, to Lucy's time, she herself may have been flat-footed, but we know from the fossil record and fossilized footprints that Australopithecus had well-developed arches as well. So the same kind of variation you see in humans today probably existed well into the past. And also the same kind of injury risks, such as stress fractures that humans have a higher likelihood of getting because they're flat-footed today, we may see in the past with something like Lucy. But we have more direct evidence for pathologies in animals that existed in the past 2-3 million years ago. For instance, there are 2 fossilized specimens, one from Ethiopia, that's from Lucy's species. It's a big male Australopithecus afarensis. And there's another funny little fossil from Kenya. And both of these also have odd angulations to them. And they're the same kind of angulations that we see in humans today who have unhealed breaks of their fibula when they're children. And so if you break your fibula today, of course, you can go to the doctor and get a cast and it heals properly. 3 million years ago, you don't have this option. And so these individuals give us good osteological evidence that ankle breaks were, I don't want to say common, but certainly more common than what we see in, say, African apes. This slide got a little messed up, that's okay. That's the number to look for here. African apes have a very low percentage of healed fibula fractures. What we have in the fossil record, given the numbers that are currently present, is about 10% of the specimens we have in hand have healed ankle fractures. And so that's quite a bit. We also have evidence of osteoarthritis. There's a wonderful foot from Olduvai Gorge known as the OH8 foot, and it has osteophytic growths all along the outside of the foot and growths into the ankle region of the foot as well. This individual suffered from pretty extreme age-induced osteoarthritis. There's evidence for compression fractures in a South African Australopithecus. This is the talus here, and it's crushed into the calcaneus and fused together, and this would have happened in life. And these are things that, again, are consequences of walking in a bipedal fashion on a modified ape foot. And finally, there's an example of what could be hallux limitus in a metatarsal from South Africa. This would mean that the big toe was a little wobbly and could squish into the head of the metatarsal, forming this little osteophytic growth. The point here is that if we look back in time, these are not pathology-free ancestors. These things were suffering from many of the same foot ailments that humans suffer from today. So the whole idea of podiatry, I suppose, could go back 3-4 million years as a consequence of our walking on modified ape feet. So I want to wrap up, and the way I want to wrap up is to first say that humans are remarkable animals. The panelists here today are going to be talking about the scars of human evolution, and it's not a bunch of scholars standing up here talking about ripping on human anatomy. That's not what we're doing. What we're saying instead is that it's important to understand human anatomy through the lens of evolutionary biology, because that's the only lens through which this makes sense. If you were going to start from scratch, there's no way you'd make a foot out of 26 parts. And if you did, you wouldn't be accused of being intelligent. Thank you.
Thanks, Jeremy. Next, it's my pleasure to welcome back for a second round in the BU Dialogues in Biological Anthropology, Karen Rosenberg of the University of Delaware, who is going to talk to us about her specialty, laboring humans.
Thank you very much, Matt and Kay, for inviting us here. Okay. If you want to think of a really good example of a human characteristic that is not intelligently designed, you don't have to think further than thinking about the tricky, complicated, uncomfortable way that human women have babies. When Krogman published his article on the scars of human evolution in Scientific American in 1951, he recognized that many features that seem to be weaknesses in the human body are consequences of our evolutionary history. He's described these flaws as scars of our imperfect evolution, and in many ways he anticipated the late 20th century field of evolutionary medicine, though his writing carries the implications that evolution is a progressive process that will eventually resolve these issues. You can see that he wrote, part for part, our bodies, particularly our skeletons, show many scars of nature's operations as she tried to perfect us. One literal scar that some human women carry is a cesarean scar. as one reminder, obviously a very extreme one, of the use of culture, in this case medical technology, to ameliorate the strong selection acting on adult female and infant morphology in humans today. Cesarean section is one extreme, or maybe even the most extreme, form of obstetric intervention that extends from a midwife or close relative attending a woman during childbirth in case she needs some help, to this surgical removal of the baby from the mother's body. I want to emphasize that in talking about this, I don't mean to defend the current rates of cesarean sections, nor to argue that all cesarean sections are done for good reasons, whatever that means. In some parts of the world, cesarean sections are done very, very frequently. This is a graph showing the rise in cesarean sections in the United States over the last several years. They're done for all kinds of reasons, including a range of medical problems, emotional reasons. Many women today actually choose to have elective cesarean sections, fashion, financial incentives for doctors, convenience, cosmetic factors, and a hedge against liability. The rates in other countries outside the United States are sometimes even higher, with Italy, Mexico, and Brazil. Brazil isn't on this graph, but approaches 50%. So this is the percent of births which are delivered, babies which are delivered by cesarean section. So in Italy, 40%, in the United States, more like 30%. Although it's difficult to know exactly what percentage of cesarean sections that are done today reflect the situation that would have been under natural selection without that intervention, the World Health Organization suggests a target cesarean section rate of about 12%, shown in green at the top of the picture. Good arguments have been made that even apart from surgical interventions like C-sections, childbirth has been over-medicalized in the United States and many other countries. But it remains true that childbirth is a time in the life cycle when women and their babies are at increased risk of injury or death. Another hint at how much selection this system is under comes from figures on maternal and infant mortality. This is maternal mortality worldwide in female deaths per 100,000 live births. And this shows that in many parts of the world, maternal mortality remains very high, and in many parts of the world, infant mortality remains even higher. And the latter is actually higher in the United States than in many other developed countries. So without getting into arguments about how risky, how painful, or how awkward childbirth is for women and babies today, it's fair to say that this process, which is at best uncomfortable and at worst dangerous, is one of the kinds of human features that Krogman meant when he talked about the scars of human evolution. In fact, he even mentioned childbirth directly in his Scientific American paper. He said, "We have expanded our brain case tremendously, and there can be no doubt that many of the obstetrical problems of Mrs. H. sapiens are due to the combination of a narrower pelvis and a bigger head in the species. How long it will take to balance that ratio, we have no idea. It seems reasonable to assume that the human head will not materially shrink in size, so the adjustment will have to be in the pelvis. That is, evolution should favor women with a broad, roomy pelvis." What Krogman didn't point out was that there were other variables in the system that could be tinkered with in the evolutionary process, besides just the size of the mother's pelvis and the size of the baby's head. And I'm going to talk about some of those today. I want to say as clearly as I can that recognizing the risks and dangers that are implicit in the human birth process in no way means that I'm an apologist for the extreme medicalization of childbirth that we see in the United States and many other nations. On the contrary, I want to argue that an understanding of the evolutionary history and the selective pressures at work on the various aspects of human morphology and developmental timing that constrain the birth process help us to understand the cultural and social context in which human birth has evolved. In fact, I think some of what we've learned from the fossil record can help us to demedicalize the way that women have babies. What may be most interesting about the way that humans give birth, as my colleague Wenda Trevathan has pointed out, is that the context of human childbirth is different than in other primates. Other primates generally give birth not only without assistance, other primates generally give birth not only without assistance from other members of their group, but in isolation. But humans give birth socially, with other people around to help out. Briefly, Trevathan has argued that because of the size and shape of the human birth canal and the size and the shape of our babies' heads, human babies typically rotate as they pass through the birth canal. I want to emphasize that this stereotypical mechanism of birth that I've shown here, you're looking at the pelvis from the front with the baby's head entering the birth canal at the inlet facing to the side and then turning so that the back of the baby's head, the occiput, is to the front of the mother's body, anterior. So this is a position that obstetricians call occiput anterior. I want to emphasize that this stereotypical mechanism of birth is not the only way that babies are born, or even the only way that babies are born without difficulty, but it is by far the most common way. And importantly, from an evolutionary perspective, it's the mechanism that is associated with the lowest risks to the mother and to the infant. Trevathan argues that because of this rotation, as well as a number of other characteristics of human birth, humans benefit from assistance during childbirth in a way that other primates do not. And in fact, other primates and mammals, as I said, typically give birth in isolation. That help can come from many different individuals, as you can see in these various depictions of childbirth from around the world. Attendance and possibly intervention at different points in the birth process can help to increase the chances of a successful outcome for both the mother and the baby. This is really an extension of what Sarah Hrdy refers to when she talks about humans as a species of cooperative breeders, or when she talks about allomothers or alloparents. Human mothers and infants live and function within a social fabric in which all kinds of people who are not the mother care for and provide for children. This social fabric extends back into the life cycle, at least to childbirth, when women give birth with the assistance of others, whether they're midwives, their own mothers, their sisters or aunts, obstetricians, or even husbands. The investment of other members of the group in the process of childbirth makes it more likely that there will be a successful outcome. Of course, after birth, the demands of immature but relatively large-bodied infants for attention are very high, and they benefit from the attention of the alloparents, as Hrdy calls them. In addition to the shape of our pelvis, there are a number of other aspects of our morphology and our development that have an impact on the way we give birth. These include the size of our brains at birth, the size of our infants' bodies at birth, the breadth of babies' shoulders, the development of our babies at birth, and as I already mentioned, the extent to which we assist each other during the process of labor and delivery. The evolutionary changes that occurred in each of these left traces on the birth process that characterize how humans give birth today. Early in hominid evolutionary history, the pelvis was dramatically altered as a result of a shift to habitual upright bipedalism. This locomotor change had important consequences for the way we give birth. This figure shows chimpanzees on the left, Australopithecines, that's Lucy, in the middle, and modern humans on the right. And you're looking at the inlet, the midplane, and the outlet, the planes of the birth canal, and in the middle you can see the infant coming through. Tegan Lovejoy reconstructed the mechanism of childbirth in Australopithecines, who had a flat, wide pelvis, as transverse and non-rotational, proposing a mechanism of birth that is neither entirely ape-like nor entirely human-like. This isn't surprising, given the mosaic nature of Australopithecines, who had human-like locomotion and an ape-like brain. Generally, when people talk about Australopithecine pelvic morphology, they've assumed that because Australopithecines didn't have large brains, that they were not under selection from obstetric constraints. But the change in pelvic morphology that was required by the shift to bipedalism demanded a change in the mechanism of birth. That is, though the pelvis was dramatically restructured because of locomotion, that change had obstetric consequences. Everyone recognizes that the infant's head in humans represents a significant challenge to the birth process. But another dimension of the human body that sometimes creates difficulty during childbirth would also have been an issue for Australopithecines. Trevathan has pointed out that humans, like all apes, you can see on the bottom of the diagram, have broad, rigid shoulders. Humans have a tight fit between the birth canal and the neonate, and the changing cross-sectional shape of the birth canal means that the head typically undergoes that twist. Our neonate's broad, rigid shoulders also typically follow the same route, so that after the head has emerged from the birth canal, the body rotates to allow the shoulders to take advantage of the same longest axes at each plane of the birth canal. These occasionally create a dangerous situation that obstetricians call shoulder dystocia, in which the shoulders get stuck or impacted in the birth canal. This occurs more commonly in larger infants, but can occur in small ones as well. It can lead to a range of medical problems for mothers as well as for infants. Today, physicians and midwives often try a series of maneuvers, like changing the mother's posture, to alleviate the obstruction. And they may even resort to breaking the infant's clavicle to ensure that it can pass through the birth canal. Non-human apes don't experience shoulder dystocia because their birth canals are large relative to the size of their infants' bodies. Although Australopithecine babies had brains that passed through the birth canal in the transverse orientation shown in the diagram, their shoulders, which are at right angles to the longest axis of the head, would have had to pass through the same way. Hence, they may have experienced some aspects of the rotation of modern birth. The recently discovered material from South Africa, shown here, that's been attributed to Australopithecus sediba, includes an adult female pelvis with what the authors who describe it refer to as modern human features. They argue that these could not be obstetrical adaptations since they occur in a small-brained species. But as I've said, while neonatal cranial size is a very important part of the story, it isn't the whole story. We know that changes in the birth mechanism must have taken place by the time of Australopithecines as a result of the morphological changes associated with bipedalism, and that neonatal cranial size is not the only reason for obstetrical adaptations of the birth mechanism. It's reasonable to suppose that a bipedal, broad-shouldered species giving birth to large-bodied infants would have had different obstetrical constraints than a quadrupedal one, and hence may have had some pelvic changes to accommodate those constraints, even in the absence of a large brain. The Gona specimen from Ethiopia, which is probably Homo erectus, shows considerable AP expansion of the pelvis and the birth canal. Simpson, who described it, argued that the expansion would have allowed a female like this one to have given birth to an infant at the lower end of the modern human range of variation. You can see this is the Gona specimen in the middle. Although Gona is expanded in the front to back dimension of the birth canal compared to Australopithecines, it's at the edge of the modern human range shown in this picture, the inlet and the midplane, and those squares and circles are modern humans. Moving to size of the infant, although they may seem tiny to first-time parents, human newborns are big relative to their mothers compared to other primates. Gorilla newborns average about 2.7% of their mother's body size, chimpanzees about 3.3%, and human newborns about 6% of the size of their mothers. This fact accounts for some of the costs associated with carrying human babies around in utero and, of course, after they're born as well. Jerry DeSilva, who just spoke, has argued that this infant-mother mass ratio has characterized humans and our close relatives for a long time. You can see in this slide from his paper that all of the hominid, modern, and fossil samples he looked at had relatively high infant-mother mass ratios, except for Ardipithecus, which was much closer in this to the African apes. Humans today also give birth to newborns who have completed a small percentage of adult brain growth at the time of birth. This table shows that on average, human babies are born with brains that are about 29% of their completed adult size. Monkeys have numbers which are higher, as do apes. That is, if you look at this sort of schematic picture of human brain growth, you can see that many non-human primates, like chimpanzees, are born at the point where brain growth slows down, at that inflection point. Humans continue to grow at essentially fetal rates of growth for some months after they are born. This is what Ashley Montagu meant when he said that humans have exterogestate fetuses. We continue to gestate outside of the womb. This is possible because we are able to continue to incubate them culturally and buffer them from the environment. DeSilva and Lesnick have shown that this pattern of giving birth to helpless babies probably dates back to the period in our evolutionary history when encephalization, increase in brain size, took place. Finally, there's good evidence from modern clinical environments that it is not only physical support that helps women in childbirth to have successful outcomes. Emotional support during labor and delivery is very important too. And there's strong evidence that shows that women who receive emotional support during childbirth have lower rates of all types of intervention from clinicians, and they have shorter labors. The implication is that women who give birth without emotional support and their babies are at greater risk than those surrounded by familiar, supportive people. This is hardly surprising, given the social supportive environment in which women have been birthing for many hundreds of thousands of years at a minimum, and perhaps much more. The human fossil record shows us that the obstetrical package that we see in humans today evolved in a mosaic fashion as natural selection tinkered with a set of changing constraints set by our bipedal locomotion, our large brains, our relatively helpless but large-bodied newborns, and our ability to intervene in the birth process. The imperfect and risky way that humans give birth is, as Krogman thought, the result of our evolutionary history. But it seems to me more a trade-off between competing constraints than a scar of an imperfect evolutionary process. Our cultural adaptation in the form of social, clinical, and emotional support ameliorates the risks of childbirth and helps us to take care of the large, helpless babies that are the outcome of our particular way of giving birth. However awkward and even scary it might seem, the way we give birth and the broad network of cultural practices associated with our successful reproduction and care of our young children is an ancient and fundamental part of what makes us human. Thank you.
Thanks very much, Karen. I'm pleased and privileged to be able to welcome to the podium next Bruce Latimer from Case Western Reserve, who is a long-standing expert on the evolution of human locomotor and bipedal adaptations, who has managed to cram not one but two puns into the title of his talk to us today, A Backache of Long-Standing, an Evolutionary Perspective on the Human Vertebral Column.
Thank you very much, Matt and Kay, and thank you for inviting us. There we go. Well, walking upright is a most peculiar way to get around. As humans, we don't often think that, but it is. As far as we know, no other mammal has even experimented with walking on two limbs except us and our ancestors, our recent ancestors. Now, if you want a place in the human body that is indeed, and I'll borrow from Jeremy, made up of paper clips and duct tape, there is no place better than the back. In a recent study, a recent review of worldwide human disabilities, the lower back came in sixth, right after heart disease and cancer. That's how important this is, and that's how many of us are afflicted by this. Now, I start with this for a reason. You say, I know you're looking and you're saying, that looks like a kitty cat, and indeed that's what it is. It is a kitty cat. But in your mind, suspend disbelief for just a moment. Let's think about it as a Siberian tiger, 800 pounds of animal. Now let's take this animal and let's accelerate it to a full gallop, 35 miles an hour. When that animal leaps off its hind limbs and lands on its forelimbs, the ground, the force coming back from the ground, what's called the ground reaction, is enormous. Now we all remember back, and you remember conservation of energy. The energy has to go somewhere. Well, where does it go? Because by all rights, it's enough to explode a cat. Well, we don't see cats blown up all over, so they're doing something. And indeed they are. What they're doing is they take the muscles of the shoulder and the muscles of the back, the tricep, which we have, those same muscles, and they contract those muscles in a very special way. They elongate them, and those muscles take up mechanical energy, and they degrade it to heat, and that's how it takes up that energy so it doesn't damage itself. Now, watch what happens here. Look at that nightmare. We have totally sacrificed our ability to use our shoulder to absorb energy. It's gone. Not only that, we're hitting on one foot at a time. We have single limb heel strike. All you have to do is look at the bottom of your shoe and see where it wears out. That's a significant amount of energy. And I have this arrow to show that that energy travels up your limb and backwards. Now, what are we doing? Where are we going to dump all that energy? We can't use our shoulder anymore. So what we do, we have to use a whole series of muscles in the lower limb that will, this lengthening contraction, I hate that, but we'll call it eccentric contraction, that allows it to take that energy so we can protect our non-renewable joint surfaces. I'm not going to go into detail here, but I just want to heighten this line. That's the quadricep muscle. The quadricep is that big muscle in the front of your thigh. It attaches to your kneecap and it attaches to your thigh bone. Now, quadricep contracts in two different ways during a gait cycle. One is that when you hit on your heel, all that ground reaction is coming up your limb. How do you get rid of it? Well, you slightly flex your knee. And you flex your knee some 5, 6, and some people as much as 10 degrees. And that allows this muscle to take up that energy. And then further on in the cycle, when you're at push off, you're pushing off on the front of your foot, it contracts again, but this time concentrically, meaning it gets shorter, and that produces impulse against the ground and pushes you forward. The point here is this. We've had to make a whole series of adaptations to try to allow ourselves to balance on two limbs, one limb at a time, if you think about it that way, and also to somehow tolerate those stresses that are concentrated on one foot. Now, we've done something else too. Every step you take, we all know this, you throw your right arm forward the same time that you throw your left leg forward. So your upper body is 180 degrees out of sync with your lower body. No other mammal does that. And think of the millions of cycles that you do this. So you're constantly twisting and twisting and twisting and twisting. That's a peculiar way to get around. And you do that because you're damping that torsional load. Because by rights, that ground reaction we're talking about should spin you around. Well, this stops it from doing that. But it does have consequences, which we'll talk about. Well, now there's a human thoracic cage, and there is, of course, the spine, and there's the pelvis. We've heard about the pelvis already. Now, what I want you to note is this. Look at this is a side view, and there's a hollow, the hollow in your lower back. It's called a lumbar lordosis. No other mammal has that. That's unique to us. And that lordosis, that curve, allows us to balance our bodies over our feet. If you didn't have that, your body would be leaning forward and you couldn't balance. So that is a unique human condition. Now, we had to compensate for that, so we have a concavity here, a reverse convexity here, and then another concavity. So the whole point is we have taken our spine that should be a nice, even curve like it is in your dog or your cat, and we stood it up and we created these curves, largely for balance. This just shows the same thing, and you can just notice those little red lines. I mean, so we've got a kyphosis, what's called a kyphosis here, a lordosis here, and those have big, big consequences on how our spine works. Humans often don't recognize your spine is incredibly flexible. We don't often think about that because, you sometimes look at your dog or your cat and you think, gee, they can sure lick things that I can. Well, that's the point is they can in that one particular field, in that one plane, in the sagittal plane. But we have very, very flexible spines because we have to in order to walk like a biped. Here's an example of how we've changed. Here's a chimpanzee. They have reduced the length of their lumbar column to the point, and they've elongated these blades on their pelvis to the point of their last rib, literally almost touching that. And a chimpanzee has an incredibly stiff spine. It's a poker spine. You can't even flex it. Look at us. We have this long, long lumbar spine in which we twist and we flex as we walk. It's a very old adaptation. That happens to be Lucy, and we can already see at 3.2 million that there is a lumbar lordosis. In fact, it's probably one of the earliest adaptations that's associated with walking on 2 feet. This just shows what the lumbar lordosis looks. That's the first lumbar down to the sacrum, and that just gives you an idea of what it is. We all know if you put your hand behind your lower back, you can feel there's a hollow there. Now watch this. You've got to be impressed. No other mammal on the planet can do this. This is a unique human adaptation. If you don't believe me, go home and take your cat. No, don't do that. Don't do that. I'm kidding. You would kill the thing. What you want to do is just to recognize the fact that we can do that sort of thing. No other mammal can. But Karen just told us about the birth canal. Now, I won't be talking about getting that giant head of the term fetus through the canal. That's tough enough in and of itself. What I want you to note is this. See that? That's the sacrum. Now, the sacrum is nearly horizontal. If you were going to design a spine starting from scratch, you would make it vertical. But we couldn't make it vertical. Evolution couldn't do that because we have to maintain the birth canal. So we keep it in a horizontal position. And that is why we have to have that lordotic curve. Now watch. Now, this is just to show you that in a third term or third semester pregnancy, what happens is the fetus pulls the center of mass of the woman forward. Of course it does. And how does a pregnant woman walk? What does she do? Well, she leans back into a hyperlordotic curve, again to balance over her feet. And it requires all sorts of dramatic changes in the human spine in order to allow us to do this. And those little plates I've put in there just indicates that we actually have to change the orientation of the joints between the vertebra, but we also have to change the width between them. Notice how it gets broader and broader as you approach the sacrum. That would be the sacrum. It's a very old adaptation, as I mentioned before. This is STS-14 from Africa. Call it 3 million years old from South Africa. Call it 3 million, and it already shows the changes in those joints that permit it to do a back bend, but that's not why they're there, to permit it to create that lumbar lordosis. But there's a fly in the ointment. Here it is. And many of you, I won't say many of you, but I will say, and those of you watching this, 1 out of 20 of you, on average, do not have enough separation between those joints. Just bad luck of the developmental draw. You just don't. And what happens if you're forced into a lumbar lordosis, and I'll tell you who does this, butterfliers, breaststrokers, football players because of blocking, and gymnasts. Anybody that goes into that hyperlordotic curve in their lower back, if you don't have adequate separation, you have this problem. Spondylolysis or spondylosis, it's both ways. And what it means is that you literally pinch the back of your last lumbar vertebra between the inferior facets on the fourth and the sacrum, and it literally breaks that bone. It looks like this. Now, when you're young, it's not such a big problem because it's held in place by muscles and ligaments. But when you get old, like everything else in your body, everything goes to hell. And at that point, we have a major problem. Okay, you remember why I told you that the sacrum is horizontal because we couldn't include the birth canal? Well, that arrow indicates the gravity vector of your body. It's pushing down. Now, this thing no longer has a bony mooring. So it's being forced to slide into your pelvis. This is called, the real tongue twister, spondylolisthesis. And this is a serious, serious disability. And we're going to see more and more of this as our demographic shift. Here's another thing. We talk about those curves. Well, we know they're there. So we went through a collection of spines and counted fractures. And we counted the fractures, and not surprisingly, the most commonly fractured vertebra in the human spine is T8, right in the middle of this curve. That makes sense mechanically. And then when you change a convexity into a concavity, you have another hot spot. So what we have done is we've imposed forces on this curved spine, and it leads to mechanically fractures occurring at particular hot spots. And the type of fracture is unique. It's called a wedge fracture. And if you look at that, that's T8, the eighth thoracic vertebra, and it's actually crushed in the front. That's another view of it right there. Well, that's not enough. We wanted to go a little further with this. So we went through a series of humans, actually about 600 humans, and we CT scanned their vertebra looking for bone density. Look at this. These are humans. Those are the great apes, the chimps and the gorillas. Not surprisingly, if you look at bone density over age, humans lose. We know that. Look at the great apes. Very little bone loss, if any, and you don't see the fractures in them. So we've taken this human spine that's curved, we've not only put forces on it, but we've reduced the bone density with age, osteoporosis. And that's what accounts for this. 10 years after menopause, you break T8. 5 years after that, you break them down here at T12 and L1. And then because you've changed the curvature, you're putting force on the big guys at the bottom and they break. And this is what leads to what's called the Dowager's profile. This is why your grandmother gets shorter and shorter and her body shape changes. That's unique to humans. Now, quickly, I just want to go over this. This is interesting. We went through a lot of vertebra and we looked at bone mass versus bone volume. We have bigger vertebra. No shock there. We've known it for a while. But when you measure bone density, you find out that they're bigger, but they're less dense. Why do we make them bigger? Well, how do we do that? Well, we took the same amount of bone in our vertebra that a chimp has relative to its body size, and what we did is that we then spread it out in a bigger vertebra, and it became less dense. And that means our vertebrae are less strong than they are in chimpanzees. And then, of course, we do this to ourselves. We twist our vertebrae every step we take, and that leads to, after millions of cycles of walking and running, that this thing out here, this is a nucleus pulposus, this is a disc, and that's the annulus fibrosus, and now you're twisting it, eventually delaminates, and then what happens is you can herniate a disc. And then, unfortunately, it herniates backwards and often hits the nerve. If you live long enough, I can promise you, you will do this. And then finally, there's this thing. This is idiopathic scoliosis. This is one of the worst. Only occurs in humans. It does not occur in other mammals. And you can see how just awful that is. That's why in young adolescent women, in middle schools, they'll often check them. They'll go to the nurse that'll check looking for curvatures. So I'll end with this. If you want any area in the body that is poorly designed, it's this. And if we're looking for intelligent design, I say get a new engineer. Thank you.
Thanks, Bruce. That was great. I hope those of you out there who are watching the webcast or who are watching this as a video recording on our website are coming to the realization that these problems are problems that we're all going to confront in one way or another. Everybody in the course of their lifetimes is likely to have sore feet, aching backs, pelvic problems, and last but not least, the sort of scar of human evolution that our last speaker today is going to talk to us about, namely in our dentition. So I'm happy to welcome to the podium Dr. Alan Mann from Princeton University. who's going to talk to us on the subject, Wisdom Can Be Painful, and he should know, the evolutionary origins of third molar impaction in humans. Alan?
Thank you, Matt. Good afternoon. Thank you, Kay. Thank you, Matt, for the opportunity of joining you this afternoon to talk about something that I suspect a lot of you out there either have confronted already or will confront in the very near future. As a difference from what my colleagues have been talking about in terms of scars of human evolution that are part of later life. Many of you students know that you have had problems with your wisdom teeth, may still have problems with your wisdom teeth, may have painful situations in which the dentist has decided to extract them. And what I want to talk about with you today is, in fact, why we have impacted wisdom teeth, why we have such serious problems with them, because as my colleagues have already noted, we have a biological system that is not perfect, because evolution does not produce perfection. Evolution produces function. And as long as we understand that, we can understand many of the problems that we have heard here this afternoon. So my job is to talk about teeth. And when we talk about teeth, we want to talk about how we would live without them. After all, to know teeth is to love them. After all, how would we eat an apple? Or how about eating some meat? If you want to consume food, the place where you put the bite on evolution is right here. So for us, what we ought to be looking at is the nature of our dentition. A lot of us don't think about our dentition except when we're pushing that toothpaste tube in the morning or the evening, or when that awful day comes when you have to visit the dentist. However, teeth are really, really important. But before I get to that, I wanted to, along with Karen and others this afternoon, pay my respects to a colleague that I had when I was at the University of Pennsylvania. Krogman was a great anthropologist. As Karen has noted, his discussions of the scars of human evolution were absolutely astonishing for the early 50s. And we're back here again today to talk about what Krogman outlined to us more than half a century ago. So along with everybody else, I wanted to pay my respects to him and to let you know that what we're talking about was first proposed by Bill Krogman many, many years ago. Okay, let me summarize what I want to talk about. What I want to talk about has to do with the function of evolution. Although Darwin talked about the survival of the fittest, we are all well aware that evolution represents the reproduction of the fittest, that is, differential reproduction. And that means that very often, if you have traits, biological features that are in some ways deleterious or not as adaptive as they might be, that situation might not result in your death, but will result in decreased reproductive potential. And what I want to show you this afternoon is that with our evolution and the changes that have been developing through the expansion of our brain case and our very large brains, which have been touched upon by several people already, that this has brought about dramatic changes in our facial skeleton and in our dentition, and as a result, our dental arcade has become foreshortened, and there is very little room for the eruption of the third molar. So what I want to deal with today is this situation. Okay, to do this, we have to look a little bit at teeth. And the evolution of the vertebrate dentition is a very interesting topic. On the left here, you see the dentition of a fish. Like many early vertebrates, the teeth were fixed on the surface of the jaws. They could be spread throughout the entire jaw system. Indeed, there is a new paper that came out this week that talks about an original dentition that was actually in the pharynx, so that early in vertebrate evolution, the teeth developed as multiple series of teeth all over the jaws. They were used to grasp objects, tear a piece off this food and swallow it. Sometimes if the food was small enough, the whole object was swallowed. And you can see that on the reptile on the right, where the animal is consuming the bug, and that bug will not be chewed. Earlier vertebrates don't masticate their food. They don't chew. They grab food with their teeth, tear off a bite, or swallow the entire object whole. This is, in fact, very different from what mammals do. And I apologize, I am a vegetarian, and I wanted to point out that pigs have many human features. And of course, that dentition is not really piggy, but, you know, Kermit saw something. In any event, when we talk about the mammal dentition, we talk about dramatic changes. For one thing, mammal teeth occlude. The upper and lower dentitions meet together, and the surface structures on the chewing area interact in a way that permits mammals to grind, chop, shear food particles into smaller pieces. What this is all about is that the mammal dentition has in fact evolved as the forward projection of the digestive system. And as a result, the dentition plays a dramatic role in the processing of food rather than simply the obtaining of food. And in this, then, the dentition has changed. Because occlusion has to be maintained, the number of teeth, which are continuously replaceable in vertebrates, the numbers of teeth are now reduced to 2 sets. When you grow up, you have a milk set or a deciduous set. When you get older, that set is replaced by the permanent set. And, of course, because we are now culture bearers of some sophistication, when your permanent set begins to leave, you go to the dentist and you get some plastic teeth, and you keep going on there. But, of course, you need Poligrip, and that's not so pleasant either. However, the pattern of the dentition in mammals is such that the teeth work together as an absolute team, and that means that the teeth are very, very closely regulated in their eruption and their occlusion. And this is a very important thing to keep in mind when we talk about the way mammal teeth work. And here are a whole bunch of examples of mammals chewing. And chewing requires that the lower jaw teeth move against the fixed upper jaws, and as you chew, you masticate or chew the teeth. Now, when we look at a modern human dentition, on the right, you see a complete adult dentition, 32 teeth. You can see the pattern of occlusion on the jaws there. And on the left, you see the upper and lower jaws revealed to show the various teeth in their position. So you have the incisors, or the anterior teeth in the canine, 2 premolars, and then 3 molars. The wisdom teeth, or the 3rd molars, are the teeth that I want to concentrate on, because not only are they at the back of the tooth row, but they're the last teeth in our jaws to erupt. And of course, because of that, and because of the idea that when you reach adulthood, you become wise, then wisdom arrives with the 3rd molars. You can make your own comments about that. But in fact, what we find is that that's the last tooth to erupt, and it comes in at the very back of the jaws. Now, here is a set of images from a dental website, and it shows what dentists think about the human dentition. Notice that the 3rd molar is absent, because for many dentists, the 3rd molar represents a tooth that shouldn't be there. And it is pulled, extracted, and in many of you, I'm sure you have already had that tooth extracted. So when we look at the human dentition, we have to ask why dentists see it this way. And in fact, it has to do with the fact that The third molar, being the last tooth to erupt in the jaw, very often has no room to erupt normally. And so it is impacted or it has difficulties in erupting. And these impacted teeth are, in fact, what the problem with wisdom teeth, third molars, is all about. And as we'll see in a moment, the reason for the limitations in the dental arcade have to do with the fact that as our brains have expanded, the architecture of the brain case has changed. And the base of the brain case has expanded. The frontal lobes of the brain have expanded to the point where they overlay onto the facial skeleton, and everything has rotated underneath the brain case. And as a result, the dental arcade has become foreshortened, and as a result, the amount of space in the arcade for the teeth have become reduced. Now, you might talk about the reasons why the brain has expanded in human evolution, and there are many suggestions about that. Nevertheless, that is what's happened. And in fact, evolution has not worked on the disappearance or the problems with the third molar. Actually, the dentition is part of this facial skull complex where the jaws have reacted to changes in the brain case. And this has resulted in this malformation. So, when we look, for example, at a panorama of a young adult dentition, and one that maybe many of you have already had at the dentist's office, what you see, the right side and the left side, you see, for example, here, the upper right third molar, it is erupting, but it is so squeezed that it will not, in fact, properly occlude with the lower dentition. Over here, you see the lower left wisdom tooth is actually horribly impacted. Notice that it's horizontal. There's simply no room for it. And what's going to happen here is that the roots, as they develop, are going to intrude into the mandibular canal, and that's going to produce constant and some very debilitating discomfort and pain. And that, in fact, is a very serious issue. You might look and see that there is also an impactation on the upper left molar as well. So here you can see some of the very common attributes of impacted third molars. And here I'm just showing you a number of x-rays of impacted third molars in this case, in this case, in this case. And here, the third molars are, in fact, growing into the second molars in front of them. Here you see that they destroyed the root. Here you see an impactation that will, in fact, destroy part of that root. Here you see the crown being destroyed and decay, a carie developing there. Here, the same thing. With many of these, you get the development of crypts that form with cysts and other problems which create a great deal of discomfort. So impactions are a very serious issue. And one of the things that we know happened in human evolution is that sometime in the past there was a random genetic mutation. We're not quite sure exactly what that mutation was all about. We believe that on the basis of clinical studies of HOX and homeobox genes, that is, the limited set of genes that govern and regulate the early development of fertilized eggs into actual complex animals, that in fact these genes can have a very dramatic effect on the way by which the teeth develop. There are many malformations now that are known where a single change, an SNP, a single nucleotide polymorphism, in fact can produce a change so dramatic that all the dentition is gone. It also can impact the facial and cranial skeleton, and in fact produce a lot of disease factors as well. So, several thousand years ago, as part of our genetic heritage, there was a random mutation not associated with this kind of very general malformation, but resulted in the cessation or the actual disappearance of third molars via the lack of calcification. And we have 2 specimens from the Middle Pleistocene of East Asia where there is agenesis of the third molars in these individuals. So that, in fact, this is a very serious issue for us to contemplate that this began very early on. We also know that there are many short-faced monkeys and the gibbon that also show some agenesis of the M3s. So, what is this all about? Well, when we look at the human brain case and the face underneath the brain case, the large brain overlapping the face, the difference between the very projecting face with the small brain case behind in apes and humans, we realize that as human evolution has produced a very large brain case, the face has moved underneath. The difference in the architecture of the base of the brain case in apes and the very much expanded and larger brain case in humans has produced this kind of change. So what we have then is an enormous pattern of change in humans, and it is in fact, as you can see here in this chart, that the percentage of individuals and populations with lack of one or more third molars can be extraordinary, and you can see population variation up to 44%. We can also see other factors involved in this problem. For example, the upper lateral incisor shown here and the second premolar. When you have agenesis of the third molar, you also very often have lack of those teeth as well. Another factor in the shortening of the face has to do with the displacement of the lateral incisor, which you can see here in this young woman and in the picture of her dentition on the right. Other factors include when you do have upper third molars, you have, in fact, not the normal four-cusp 3 molar that we see in our ancestors, but a very foreshortened tooth that, in fact, is much shorter. So, in summary, we can say that with the development of a large brain, the facial skeleton changed, foreshortening the amount of room in the arcade for the dentition. As a result of this, we had dramatic developments in the initiation of genetic change that brought about the lack of calcification of the third molar, and that this, because it was adaptively useful, spread in frequency through the population. So, we might ask a very pertinent question, and that question is, how might this increase in the frequency of third molar agenesis come about? And my plausible scenario might be here. One evening, a partner in a relationship suggests a bout of reproduction. The other partner, plagued by an impacted third molar, which is painful enough to be distracting, says, "Not tonight, dear, my jaw is killing me." And in fact, that's enough to dramatically change the adaptive fitness of these particular genetic variants and produce an increase in this particular factor. And of course, then, with the development of medical intervention in the developed world, positive selective value of agenesis has been reduced, but in the developing world, it remains a scar of human evolution. Thank you very much.
Thanks a lot, Alan. Those are sober reflections about the impact of third molar impaction on reproductive fitness for Valentine's Day. And I'd like to thank all of you for watching our unusually long and interesting webcast today. And I hope that you'll be able to join us later on in half an hour at 5:30 this afternoon here in Hillel House on Bay State Road on the Boston University campus for a public roundtable discussion with our panelists today and with a couple of other participants who will answer your questions about the parts of your body that don't work to your satisfaction, because we're happy to have you come and complain about them. We'll learn something from it, and it's probably the only office in town that's going to want to listen to complaints on that score. So come and join us if it's Valentine's Day 2013. Come and join us today at 5:30 here in Hillel House. Ask your questions, listen to your answers, and come and join us afterwards for a reception with our panelists and participants where you can talk to them on your own time and ask your own questions privately. We'd be delighted to see you here, and again, we thank you for your participation.